Welcome once again to tutorial on the BJTs, and in this tutorial video we're basically going to teach you how to create, or rather, well, how to use a BJT as an amplifier. So before we go into the details, let me just tell you in the beginning that if we're just planning to use a BJT as an amplifier, then the most commonly used BJT operational mode would be the common emitter mode. Okay, so I'm just going to pen it down over here. Okay, there you go. So the common emitter mode is the most widely, let's say about 90 to 95% of the cases where you can use a BJT as an amplifier, well, employs the common emitter mode of BJT operation. But the question is, why do we need the common emitter mode while, well, creating an amplifier out of BJT? Well, that's exactly what we need to answer over here. So it's because of some reasons I'm just going to show over here. So reason number one. The common emitter mode provides high amount of current gain, okay, which means that if you would apply a signal at the BJT's input, okay, then you'd probably get a larger amount of current, okay. If there's a well, let's say your signal is quite weak, and well, let's say you just did the necessary things to, well, forward bias the BJT's emitter junction as such, with a little amount of current. But that little amount of current would be converted into quite a larger amount of current at the output whenever you get your output signal out of the BJT while operating it in the common emitter mode. So the CE mode providing us with high current gain is the very first criteria of the reasons. Okay, so point number two. The common emitter mode also provides us with, well, high voltage and power gains. So you could just understand that. Well, as you've seen in the previous tutorial where we just compared the various BJT operating modes, over there we told you that, well, in the common emitter, or the CE mode in short, the voltage gain is quite high, okay? And if the current gain being high and the voltage gain is high, so it's quite natural that the power gain would also be high. So these are the very, very first, reasons why we choose the common emitter mode as the most suitable candidate. Okay, next comes point number three. Now we have moderate output versus input impedance ratio for the CE mode, or rather the common emitter mode of BJT operation. Well, the fact is that, well, in this, in the common emitter mode, the approximate ratio, output versus input impedance ratio would, approximately be about, let's say, 50. Okay, generally this is supposed to be the ratio. It could vary here and there, okay, so that's not a big deal. So the fact is that due to such a perfect value of the output versus impedance, output versus input impedance ratio, the CE mode is, quite an ideal one for, cascading in stages, okay. Now, if there's an amplifier where we would require, quite a high amount of gain, which a single transistor could not provide, then we can, well, cascade several common emitter mode stages, okay, so that we can get the requisite amount of gain. Okay, so now this this impedance ratio that we're getting over here, it's quite moderate, and it just helps in cascading of the stages. But in the other modes of operation of the BJT, what happens is that it's just often seen that the output and the input impedance ratios, either they're too large or too small. So cascading becomes a big issue, and they don't perform well whenever they're cascaded due to inefficiency resulting from the fact that, well, due to gross mismatching of the outputs and inputs while coupling. Okay, so due to these basic three reasons that we've just pointed out over here, the common emitter mode is the most suitable for use as an amplifier. Okay, so now that said, we will kindly, we'll just slightly move on to the other part where we will discuss how to configure a circuit out of a BJT in the common emitter mode to use as an amplifier. Okay, so here we have a circuit diagram where we can get to see an NPN type of BJT, well, configured in the common emitter mode of operation. Okay, so on the output side, as you can see, well, we have here a resistor known as RO. Now RO represents the output resistor. So let me just write it down over here. So this represents the output load resistor. Yeah, that's better. That's more perfect over here. So the load resistor is any kind of output device, or rather any kind of output appliance to which we're basically going to supply the or rather across which we're basically gonna obtain the amplified output voltage. Okay, so that's exactly what we're trying to do over here. So now if we would just care to apply a sinusoidal input signal at the input loop over here. Okay, there you go. So now let's just call this sinusoidal signal source as S. Okay, so now this particular sinusoidal signal source, what it does is it basically supplies a sinusoidal signal at the input. Now, while we're just trying to use the BJT as an amplifier, it's quite natural that we shall use it to amplify, physical quantity, like say, for example, sound and speech, music, whatever. So all these quantities are basically AC in nature. Okay, so we're just using an AC source over here because we want to see how a BJT could amplify a any AC voltage signal. Okay, so now that we have this at the input, so it's quite natural whenever the signal would be quite high, the base emitter junction would be forward biased. So let me just first draw the waveform over here. So let's say that if we have this particular sort of waveform, okay, so I'm just doing that with red over here. Let's say the input signal has this sort of a sinusoidal waveform. Okay, not a problem. So in that case, if we're just applying this particular voltage signal, which is, let's say, very, very small in magnitude, at the input terminal, that's the base terminal of this BJT in the CE mode configuration. Okay, and now we have the voltage source known as VBB. That's basically, forward biasing this base emitter junction, okay, so that the signal may pass unhindered into that of the BJT. Okay, and at the output end, we also have the biasing voltage source that's known as VCC, as you can see over here. Okay, so now whenever this sort of input signal would enter into that of the base terminal of the BJT, it's quite natural that the input sinusoidal signal would just add up while it's in the positive polarity region. Okay, while it's in the positive half of its half cycle. Okay, then the voltage source, the bias voltage source, that's VBB, and that of the input signal would just add up in magnitude and would cause forward biasing of the base emitter junction. So we'd basically have okay, I'm just gonna write it down over here. So we're basically gonna have a voltage of, I'm just gonna write it down below. Let's say VBB plus that of this positive half. Okay, so let's just call this one as, okay, let's just call this particular peak voltage as, let's say, VO. So we just, no, not VO, sorry there. We're just going to call it, let's say, VI. Okay, so we're just going to have an input voltage of VBB plus that of VI falling at the, across the base and emitter terminals. So this particular voltage that's just going to fall across this, across the base and emitter terminals would forward bias this emitter junction and would cause an input current which is also quite small in magnitude entering through the base region, and that now causes that basically triggers the recombination process within the base region that would further attract electrons from the emitter region to come into the base region, and that should cause a current to start flowing in through the BJT. Okay, so now the current that's going to flow through the BJT would be coming from this particular voltage source VCC from the output terminal. So whenever we start the recombination process over here, okay, so then there will be a current coming from the collector terminal if we just take the conventional currents direction. So there will be current coming from the collector terminal entering into the BJT and finally come out of the emitter terminal of the BJT as well. So now this particular phenomena leads to what? It just leads to a larger amplification of this input signal. Why? It's because of the fact that in case of the CE mode of BJT operation, we came to know back in our previous tutorial on the comparison of the BJT modes that the output current, that's the collector current, which is going to flow, somewhere in this direction, okay, is basically going to cause, or rather it's basically obtained as beta IB plus that of ICEO. So here ICEO, since it just represents the leakage current, which is quite insignificant over here, but the fact that IC is about beta times that of IB, this particular term, this one represents the fact that since beta is very large, I'm just going to pen it down over here. Now since beta is very large, let's say about 100 times larger, so it's quite natural that if beta is non-zero quantity, then it's gonna it can be as large as 100. Okay, so it's just gonna cause an output current flowing through the output loop of this particular circuit, which is about 100 times larger than the base current which we're getting over here. Okay, so now that's quite interesting. So if we have the base current in the let's say in the milliamps range, then we could easily get the the collector current in the close to the ampere range. Okay, now an output current, that's the collector current over here in the ampere range, means that that's a lot of current flowing. So if we would require higher amounts, then we can use a BJT with higher values of beta. So as I said in the previous tutorial that beta can be as large as 300. So if we just use a suitable BJT which has a sufficiently large beta value, then the output current could be as large as 300 times that of the input current over here. Well, that is quite large, and that would basically cause an voltage drop across this particular resistor, which we call the output load resistor RO over here. And now this particular voltage source, that's VCC, is going to supply a current that's going to flow in somewhat this particular direction. Okay, and that would cause a voltage drop of this type of polarity as I've just mentioned over here. And if we just take the output represented by the symbol VO, which represents the output voltage across that of the A and B terminals, okay, in with this sort of polarity over here. Okay, kindly don't mind that the figure got topsy-turvy, so just kindly don't mind that. But if we just take the output voltage across the A and B terminals over here, then we are basically going to obtain an output voltage that would be several times larger in magnitude compared to the magnitude of the input signal over here at the input loop. So the output signal is going to look something like this particular figure that you're seeing. So if you just compare the amplitudes of both the the input and the output, if we just go back again, let's just take the the amplitude of this particular input signal as, let's say, let's just take this amplitude as, let's say, Vm. If the amplitude of the input signal is Vm over here, then we're going to obtain the output signal's amplitude as something equals to, I'm just going to pen it down over here, we're going to obtain the amplitude of the output signal as approximately equals to about beta times that of Vm. So you can see that the output signal is amplified beta times. Now beta for a transistor operating in the CE mode is obviously represents the current amplification, or rather the current multiplication factor. So as a result, for the fact that the beta could be as large as 300 times, so we can get an output signal having an amplitude of about, let's say, 300 times more than that of the input signal. Now that's quite impressive. Now here we have just shown the graph for the output voltage as such, but if we were to show the graph for the output current versus that of the input current also, then the graphs would be similar. And in that case, only the V's would be replaced by I. So if we just take, for example, that the input current is, let's say, represented with the with the symbol I over here, and it has an amplitude of, let's say, Im. So in that case, the output current that we're going to obtain at the output loop across that of the output resistor, that's going to be, about a beta times larger than the amplitude of that of the input current signal. Okay, so that just basically gives us the foundation for getting the concept of how a BJT could operate as an amplifier. So this particular value of beta does all the trick. Okay. Also notice the fact that in case of the input, the input waveform over here that we've just drawn over here, okay, the wave is just centered about the mean zero line. Okay, but while we just look at the output wave over here, it's just much higher above the mean zero line. Now why is this so? It's because of this particular bias voltage source which we have at the output loop over here. It's because of this bias voltage source. It supplies a certain amount of DC current through the the output loop, and that amount of DC current that's being supplied from this particular voltage source VCC in order to keep the collector junction of the transistor at a reverse bias. So that basically will causes a DC component of the current to be mixed up with the AC signal current. I mean the AC component of the signal current that just enters into, or rather just flows through the outer the output loop of this BJT configuration. Okay, so now if we just take a look over here once again, then we can just say that this particular part is actually the IDC, or rather we could just call it the IC. That's the collector current that's basically flows from that of the bias voltage source VCC throughout the collector loop as the bias current, which is of course a DC value. So if we would just before taking the output from this across that of the resistor RO, if we would just connect a capacitor C over here, then possibly it'll be easier for us, or rather we can just basically obtain the signal, the output signal, that is at the mean zero level, much like this particular waveform as you can see over here. Now, how did this happen? What did the capacitor do? Okay, let's just once again refer to our diagram. Well, the capacitor, if you just refer to its properties once more, then you'll understand why this happened. It's because the capacitors, they don't let pass DC current or voltage components through themselves. So what they do is that they would just let pass the AC components otherwise. So what happens is that whenever we connect the capacitor over here, then the capacitor lets pass the AC component of the output signal, and that's why we can get this AC signal, which is just the amplified version of the input AC signal at the mean zero line. So that's exactly what we have over here. Okay, and this should be the case with that of the input and output voltages also. Therefore, if we were to switch back to our voltage, if we were to again work with the input and output voltages, then this is what we should obtain for the output section. Yeah, there you go. That's the figure. Then this is exactly what we should obtain for the output section once again. Okay, so let's just wrap it up over here, because now I've just given you the foundation of where you can basically understand how a BJT works as an amplifier. Okay, so see you back in the next tutorial, and till then it's just going to be a short goodbye for now, and thanks for watching.